Welcome back to SSL TLS lecture series. This is part 6 and I am Saravanan learning along with you. And today we are going to discuss quickly about the advanced encryption standard, the AES algorithm. Then we will see block cipher mode of operation. In particular, we will discuss about the electronic codebook mode. Then we will look at the role of the initialization vector as well as what is meant by non. Both are same, IV or non. Then we will also go through the cipher block chaining mode of operation. Okay, so let's get started. When the theoretical attack started with the digital encryption standard, the NIST, the National Institute of Standards and Technology in US, they announced a call for proposal is a public competition. It started sometime around January 1997, and the purpose is to come up with an alternate algorithm to replace the DES algorithm. This alternate algorithm is going to be called as advanced encryption standard. The requirement for this algorithm is it has to support at least the block size of 128 bits along with a key size of 128 or 192 or 256. So that is the requirement for this competition. The block size should be at least 128. Then it should support 3 different key sizes. It should be faster both in hardware as well as in software. So this is a worldwide competition. So different cryptographers from different countries join this competition. Almost 50 different teams participated in this competition. So in the year, unlike the previous time in DES when they announced the competition, NSA was the main guy who scrutinized the algorithm for security and other things, right? But this time they changed their technique. The NIST changed their technique. All the algorithm which came for competition, they put openly for the public to see, and each team after submitting their algorithm, they downloaded the remaining 14 competitor algorithm and start scrutinizing extensively. Like everyone is attacking other team to figure out what loopholes their algorithm has on all such loopholes they were publishing. In addition to the fellow teams, the NSA, National Security Agency, they also scrutinized all the algorithm. So all the competitor as well as the NSA went through all the algorithm that came for the competition. So roughly in 1998, they had a first conference to discuss the shortlisted candidates. So it didn't ended in 99. So they had one more conference in 1999, and finally they shortlisted almost 5 algorithms as the finalist algorithm. So all the 5 algorithms are almost equally capable, and finally they have to decide one winner, right? So they were looking at the efficiency, performance in hardware and software, flexibility of the algorithm, and finally they decided to select a winner. The winner was called Rijndael algorithm. Rijndael. It's a bit difficult. So we will see why this Rijndael name came. So basically this Rijndael algorithm was submitted by 2 cryptographers from Belgium. In Belgium they have a lot of languages, right? So one of the languages is the Dutch language. So this pronunciation of these two author names actually is in Dutch. So one of the author of this algorithm is Vincent Rijndael. I am just pronounce it like an English word. So this pronunciation originally is in Dutch pronunciation. And the other author of this Rijndael algorithm is Johan Damon. Again I am pronouncing it English. So this guy is actually original pronunciation is in Dutch. So these two guys are the inventor of this so-called Rijndael algorithm. So it's something the pronunciation looks something like the Rijndael, or some even consider it something like the Rijndael, something like that. So roughly this is what most of the time I hear, Rijndael algorithm. Okay. This guy, the Johan Damon, he is very famous not only for AES, he is also the designer of the SHA-3 algorithm. In fact, this year in 2017, he got an award from the Real World Cryptography for designing both the AES and SHA-3 algorithm. Okay. So the AES, although the competition was announced by the American government, the algorithm itself was designed not by the American but by the Belgium guys. Okay. So roughly in October 2000, roughly in October 2000, they announced the winner, and the winner algorithm was renamed to AES. Technically, if you look at right, there is a slight difference between the Rijndael and the actual standard AES, but for most purpose, you don't have to worry about those fine differences. Okay. So the following year, in November 2001, finally the NIST published this standard in the form of Federal Information Processing Publication 197. Almost all the project, when you get a US federal projects, right, you will see that it should support the 197, right? You might have seen. So for the AES algorithm, the block size for the algorithm is a fixed block size. It's always going to be 128, and hence the output is also going to be 128. This is your plain text, this is the ciphertext, and the key that it should support, I told you right in the call for proposal, they said it should support at least 3 different key sizes: 128 bit, 192 bit, and 256 bit. So this is the AES algorithm. Most of the time when we discuss the DES, triple DES, AES, we always notice that if the input is n bit, after encryption the output is also n bit, right? This is not a standard. It so happened whatever algorithm we saw, both the input and output was equal. There are some algorithm where the output is greater than the input. If the input is n, the output might be greater than the input. So don't assume that input and output are always equal. Okay. It so happened the algorithm that we took, that is TES, triple DES, AES, in these algorithm both input and output are same size. The block size is same. Okay. This AES algorithm, as of today, there are no practical cryptanalytic attacks available, which is better than the brute force attack. So this is totally safe. In fact, the NIST has decided to use it for top secret, the American top secret. So for top secret, usually they will use AES 256 bit as the key size. When we learned about the block cipher, I told you right, in a typical block cipher, we use what is called a secure permutation. So a block cipher is nothing but performing a secure permutation, right? If you remember one-to-one mapping that I discussed in one of the previous episodes, I told that along with the secure permutation, in order to use the block cipher in real life, you also need what is called a mode of operation, right? So what exactly is the purpose of this mode of operation? Let's say you have, this is your input, right? This is your block cipher. It can be anything, AES or DES or anything. Let's say you provide the input x1, x2 and x3. Then obviously your output you will get block y1 and then block y2 and then block y3, right? This is you are encrypting using key k. So this is how a typical block cipher works. If you, let's say if the input, let's say I am assuming a 128 bit block cipher. If my input, I am dividing my input like this. So the last block, let's say you have 130 bits in your last block. That means you have to pad the block. This is the 2 bits, right? So this is your 128. You have 2 extra bits. So this 2 extra bit you cannot do a block encryption. So what we will do is you will add necessary padding so that the resulting block will become 128. Whenever your block size, right, is less than the required bits, that is 128 bit in this case, you have to perform a padding. So mode of operation will handle this so-called padding. Not only that, if you have multiple messages, we know how to encrypt one message, right? But if you have multiple messages like this, mode of operation will know how to handle multiple messages, as well as when there is a need for a padding, it know how to perform the padding. For example, mode of operation helps to hide the statistical pattern that is there in the plain text. So don't worry about this. We will see an example what is meant by a statistical pattern and how the statistical pattern is preserved in the ciphertext also. Okay, we will see an example for it. So the first mode of operation that we are going to see is what is called a textbook mode of operation, that is electronic cookbook mode. We call it, oh sorry, not cookbook, electronic codebook mode. Electronic codebook, CODE code BOOK book. Okay. So in this mode, all we do is you give the x1, you will get y1, right? You give x2, you will get y2. That's all. So it's something like a parallel. So let's say you have 3 blocks, right? This is your first block. This is your second block. This is your third block. You encrypt using EK, using the key K. This is encryption using the key K. So this is your plain text input P1, this is your plain text input P2, this is your plain text input P3. After encryption you get ciphertext C1, ciphertext C2, ciphertext C3. Here there is no connection between one block and the next block, right? It's completely independent, and because of that we can perform this using a parallel algorithm. That is, encryption and decryption can be performed using parallel algorithm, and hence this mode is going to be very fast. However, unfortunately in practice we will never ever use this mode. The reason is why we don't want to use this mode is, let's say you have a input, right? Let's say I will give the input x1. I told you if you give input x1 I will get output y1, right? After some point of time, if you repeat the same input x1, your key is still same, your key is still key k, okay? Again you are going to get the same output y1. That is, as long as your key is same, whenever you give the same input, you get the same output. This what we call as deterministic encryption. Deterministic encryption, okay? Deterministic encryption means as long as you don't change the key, whenever you give the same input, you will always get the same output. So what is the problem with this? The problem is it will preserve, let's say in the input if there is a pattern, right? It's going to preserve the exact pattern in the output. Even though the output is encrypted, the pattern will be same. Because if you have x1 here, it's going to provide a y1 here. If there is a repetition of x1 here, you will get exact same y1 here. That is, whatever pattern is there in the input, that pattern will be exactly preserved in the ciphertext as well. You might think, what is the big problem with this, right? Let's say you are using a AES 256 top secret encryption using the ECB mode. Even though it's encrypted, your human eye can still observe the pattern. For example, let's take a simple example of a penguin picture, right? So this penguin picture might have a lot of background with the same color. Say, let's say you have a lot of white background. So if you take a bitmap BMP format, you take the pixel values, you encrypt the pixel values using AES 256. So after your encryption, whatever the pattern you saw, the same white color, right? Everything preserved in the ciphertext as well. So let me show you a simple example for this. Okay, if you look at this picture, let's call it picture number 1, picture number 2 and picture number 3. The first picture is the original penguin image, okay? This is not the picture that I created. I just copied it from the Wikipedia. So this is the original penguin picture. So if you look at the background is full of white, the penguin stomach is white, the penguin neck is white, whereas the body is black. So all the same pixel, if you encrypt, this is the encrypted using the AES 256 in the ECB mode. Even though it's encrypted as a top secret, the human eye can still see the pattern in this, right? The ciphertext pattern you can still see. If you give to a child, after a few seconds, the child can tell this is a penguin, right? That means the input statistical property is still maintained in the ciphertext. Let's say if I use a non-ECB, there are a lot of non-ECB mode. For example, you have cipher block chaining mode, you have counter mode, you have Galois counter mode. If you use any of the non-ECB mode, you will get this. So here the output is completely random, there is absolutely no pattern. That means you must never ever use this ECB mode of operation. In real life, you should always use non-ECB mode of operation, okay? So this mode of operation, it also does the job of hiding the statistical property in the plain text, okay? It hides the statistical property in the plain text. If we don't hide, there are a lot of language experts. For example, let's say the original is a real text. No, it's not an image, it's a real text, right? In each language, there is a frequency chart available for the alphabet. For example, if you take English, we have for letter A, how much percentage it will regularly occur in the English language. For every character, you have this so-called frequency analysis. Every language has this frequency analysis table performed using millions of words used in that language, okay? So if you provide two same output, when the cryptographer analyze the ciphertext, right, if there is a repetition of output, they can use similar table and can figure out what the particular letter is using the so-called frequency chart. So they can attack one letter at a time and eventually they can decrypt the whole thing. So we should not allow to preserve the statistical property in the input in the output. That means we should never ever use ECB mode of operation. You should always use a non-ECB mode such as the CBC mode or the counter mode or GCM mode, and lot of other modes are available. Okay. Not only that, the ECB mode has another problem, that is, if the underlying protocol which uses the ECB mode, if it doesn't have the mechanism for integrity or authenticity checking, then you can perform what is called a replay attack in ECB mode. So let's give a toy example. Okay, a toy example. So let me clear the screen. Let's say you have a bank, right? The bank has a very simple protocol. So what they will do is, if a person transfer from one account to another account, they use this simple protocol. This is your from bank name. This is the from bank name. This is the bank name. This is the from account number. Whoever is exchanging from account number. This is the to bank name. Okay. This is the to bank name. This is the to account number. And finally the amount that you want to transfer. Let's say this is a toy example. In real bank it might be much safer than this. So in this toy example, there is no integrity authenticity checking mechanism. So let's for the time being assume each of this column is a one block, right? So this is block 1, this is block 2, this is block 3, this is block 4, and this is block 5. So after encryption, what will happen? You will get y1, y2, y3, y4, y5, right? Now I am the attacker. What I am going to do is, I start two bank account A and B. I start two bank account. I just transfer $1 from this account to this account. I will observe the encrypted text 1, 2, 3, 4, 5. Okay. I perform this $1 transaction several times and I will collect the ciphertext data. Now after some point of experiment, I know that this is block Y1, this is block Y2, this is block Y3, this is block Y4 and Y5. So I know that this is my two account, this is my two bank, this is my two account, right? This is my amount. So what I will do is, let's say later some point of time, our Alice and Bob transferring money. Okay. So you capture the ciphertext, you intercept the ciphertext. In this ciphertext, this is the Y3, Y4, right? You remove this fellow, and what you do is you cut and paste your Y3 here and you cut and paste your Y4 here. That is, you are changing the block. You remove the cipher block from your interception and you put the one you already captured, right? That you can put. That means whatever Alice is transferring, the money will come to your account. This is what we mean by replay attack, when there is no integrity or authenticity protection in the underlying protocol. So because of all these reasons, you should never ever use the electronic codebook mode. Okay. So if I want to prevent from the so-called statistical pattern appearing in the output, what can I do? That means every single time you encrypt with the same key, you should not produce the same output. You should produce a different output, right? So let's say I have a block here. I am giving x1 as my input. This is my key k. So I will get y1 as output, right? If I should not get the same output, if you repeat the input, what I can do is I can add a random number here. Okay, I will add a random number here. So first time I will get y1, second time I will change the random number. Instead of r, I will give r2 for the second time. So automatically my output will change to y2, even though the input is still same. Okay. So third time I will change this random number to r3. So even though my input is same, now I will get the output as y3. That means with the help of this random number, even though your input is same, your key is same, your output will keep on changing every single time. This is what we mean by probabilistic encryption. Probabilistic encryption. Okay. In ECB mode, we learned it is a deterministic encryption, meaning if you don't change the key, as long as you give same input, you will get the same output. Whereas in probabilistic encryption, even though you don't change the key and input, we include an additional random number, and because of that, every single time our output will be different. This additional random number has a special name called initialization vector, or it is also called nonce. The word nonce itself has the meaning. It means number used only once, n once, number used only once. Okay, for a given key, number used only one. You should never ever repeat the nonce. The moment you repeat a nonce, the underlying block cipher will become vulnerable. Okay. Okay, so we learn the purpose of the initialization vector and nonce, both are same. That is to convert your block cipher into a probabilistic encryption. Okay, that is even though the key is same, input is same, because the IV is keep on changing, your output will change. Okay. Okay. So let's learn one of the most famous mode of operation called cipher block chaining mode. So in cipher block chaining mode, you typically have your input. Let's say this is your input P1, right? First block. You will provide a initialization vector. Then you will take a XOR of both these things. Remember, XOR itself is like an encryption, right? One of the past episode we learned XOR can act as a very good encryption function, right? Then you take the output. This output you will do your encryption. That is whatever your DES, AES, whatever is your block cipher. You will not encrypt directly the plain text. Instead, you will mix both the IV and plain text, and then you perform the encryption of the result. So then you will get your ciphertext. So this is your ciphertext C1. For the next block is the same. So you have the next block which is P2. You will get your IV. So let's call this IV1, right? So this is your IV2. So you perform a XOR of this. You take the output and then you encrypt this output using whatever your block cipher. You get your ciphertext C2. But the only difference is here we will not pass a IV2. Instead, we will take this output and provide this output as the IV for the following block. That is, your IV2 is nothing but your previous block ciphertext. Okay, the previous block ciphertext will become your IV2. So same thing for the following block, you will take this your previous block output and this fellow will become the IV for the next block. So because you are taking the cipher and then you are making a chain out of it, this mode is called cipher block chaining mode. The beauty of this mode is because you are making a chain, right? If you make one bit of change in your input, it will affect all the following output, right? If you make one bit of change, because it changed for all the blocks will get affected. So that is one good thing, because if you disturb anything, everything will get affected. Okay. So CBC is one of the popular mode used in SSL TLS. Nowadays, the trend is to move from all these so-called CBC, counter and all this mode to what is called the authenticated cipher. We will discuss about it in a future episode. So for the time being, we don't go into the so-called authenticated ciphers. Okay, so don't worry about this. There are some special mode available for them called AEAD. The cipher itself is called AEAD cipher. All these things we will learn in a separate episode, so don't worry about this. So here we learn what is called a cipher block chaining mode of operation. I think we can stop here. In this episode, what we have learned is, in the beginning we saw how the AES algorithm came into picture. Basically out of a NIST competition, worldwide competition, from 15 algorithms they shortlisted 5 algorithms and finally Rijndael algorithm became AES algorithm. This fellow supports a block size of 128 and a key size of 128, 192 and 256, right? Okay, so far no attack exists for AES, so it is totally safe. Even the US government top secrets are encrypted using the AES 256. Okay, then we also saw what is called a mode of operation, because in block cipher secure permutation alone is not enough. In order to handle multiple message block and also to handle the padding operation, you need a mode of operation. The mode of operation also helps to hide the statistical properties in the input, right? It can hide the statistical property in the input. We saw an example using the penguin. We also learned that if the underlying protocol doesn't use the integrity or authenticity check, and if you use ECB mode, you can perform a replay attack. So because of all these things, we should never ever use ECB mode of operation. For all practical purpose, we will use non-ECB mode of operation such as cipher block chaining mode, counter mode, GCM mode, etc. Right? Then we also learn how the cipher block chaining mode is working. Okay, we will stop here. Thank you for joining with me in episode 6. I will see you again in the next episode. Thanks.